Hi, welcome to Algo Guide. I am Praveen Kumar. Today we are going to discuss the topic recursion. We look at what is recursion, why do we need to go for recursion, and how a recursion can be implemented. What is recursion? It is a method of solving a problem where the solution depends on solution to smaller instances of the same problem. Let us understand this with an example. If I were to implement a method called power, which takes two parameters. The first one is the base and the second one is the number n to which the base has to be raised. This can be represented as b raised to the power n. Now if I call this method power with a value 2, 5, the value of base is 2 and the value of n is 5. This can be represented as 2 raised to power 5. So this is nothing but 2 multiplied with itself 5 times and we get the value 32. Now this is the larger problem. So if I were to represent the larger problem as a smaller instances of the same problem, I can represent this as 2 multiplied by the power method with base being the same. Now the value of n I can decrement by 1. That is, now it becomes from 5, it becomes 4. So I am representing the larger problem as a smaller instance of the same problem. And when the solutions of the smaller subproblems, right, gives the solution to the overall problem, this is nothing but recursion. Now this power with base 2 and 4 can now be represented as 2 multiplied by power method with now instead of 4 now we decrement the value by 1, it becomes now 3. This can further be represented as 2 into power 2, 2. This can further be represented as 2 into power 2, 1. Now when this method is called with the value of n as 1, it returns the value 2 because this forms the base case. So whenever the value of n is 1, you return the value of the base. So in this particular case, it gives the value as 2. 2 is returned. And it is returned at the place where it was called. So it was called here. So now this 2 is multiplied with this value of 2 and we get the value as 4. And this 4 is returned at the place where it was called. It was called here and this would have given a value 4. And this 4 is multiplied with this 2 and we get the value as 8. And 8 is returned at the place where it was called and this gives a value 8. So 8 into 2, 2 is multiplied with 8, we get the value of 16. And 16 is returned at the place where it was called. So it was called here. So 16 is now multiplied with the value 2, we get the value as 32. And 32 is returned, which is the result of power, which values 2 and 5. Let us visualize the power method with value 2 and 5 in the form of a solution tree. Now when the method power is called with the base 2 and the value of n as 5, when it is called, it can be represented as 2 into power 2, 4. The value of 5 is now decremented 4. Now this method is now called the calling function. Is pushed into the stack. So this forms the calling function and this forms the called function. So whenever a function is being called, the calling function is pushed into the stack and the function is called. And when the function returns whatever the functionality computes and returns the value, it returns at the place where it was called and that address is popped from the call stack. Now this 2 into power 2, 4 internally now calls the power method with the value of n decremented by 1, which is now 3. And this is now pushed into the stack. So this process repeats till the value of n is 1. So the value of n when it 1 is 1, this forms the base case, and this 2 is returned at the place where it is called. And once it returns the value 2, this function is removed from the call stack. And this value 2 is multiplied with the value this 2, and this results in the value 4. And this 4 is returned from the place it was called. It was called here. So this would have given 4 into 2, this would give the value as 8. And this 8 is returned, and this is removed from the call stack. This method is removed from the call stack, and 8 is returned to the place it is called. It is called here, so this gives the value 8. 8 is now multiplied with this 2, we get the value 16. And 16 is returned, and this function is removed from the call stack. So 16 is returned the place where it's called. So now this 2 is multiplied, 2 into 16, this gives us the value as 32. And 32 is returned, and this method is removed from the call stack. And 32 is returned to the place where it's called. So the power method with 2, 5 returns 32, and then it is also removed from the call stack. Let us look at the algorithm for this implementation. So when the power method with base b and the value of n, that is power raised to n, is called, so this forms, the first statement forms the base case, that is, if the value of n is equals to 1, you return the value of base. Otherwise, you return the value base multiplied with the power method, now with the value of n decremented by 1. Let us look at the time complexity of this approach. When you look at the solution tree, the height of the solution tree is n. Each time the function is being called with the value of n decremented by 1. So there were n function calls, hence the height of this particular tree is n. Therefore, the time complexity of this implementation is big O of n. Let us look at the space complexity. So when we look at the call stack, at the maximum, the values that the call stack will have will be n function calls. And when we look at the function call, we are not storing any extra space for each of this function call. Hence, the space complexity of this implementation will be big O of 1. Let us look at another example, which is to find the Fibonacci series for nth term. A Fibonacci series is a mathematical series where the value for a given term depends on the sum of its previous two terms. The 0th term and the first term is always having value 0 and 1, which is a fixed value, and the subsequent terms value will be based on the sum of its previous two terms. So if I were to calculate the value for the 5th term, this will be the Fibonacci series for the 3rd term plus the Fibonacci series for the 4th term. The value for the Fibonacci series for the 3rd term is 2. The value for the Fibonacci series for the 4th term is 3. So these two are added. So this will be the sum of this will be the 5th term, will be the value for the 5th term. Let us visualize the Fibonacci series function with a value 5 in a form of a solution tree. Now f of 5 is internally calls f of 4 plus f of 3. That is, the value of f of 5 depends on the value of f of 4 plus f of 3. Similarly, f of 4 internally calls f of 3 plus f of 2. F of 3 internally calls f of 2 and f of 1. Similarly, f of 3 calls f of 2 and f of 1, and f of 2 calls f of 1 and f of 0. F of 2 calls f of 1 and f of 0, and f of 2 calls f of 1 plus f of 0. Now f of 1 and f of 0, these are the base conditions. So whenever the base condition is met, it returns the value of that particular base condition. So f of 0 returns 0, f of 1 returns 1. So 1 plus 0, that is added, and f of 2 will have the value 1. Similarly, f of 1 is the base condition, it returns 1. F of 2 is already computed with the value 1. So 1 plus this value 1. So this will give you the value 2. F of 3 is 2. Similarly, f of 1 here returns 1. F of 0 returns 0. The sum of these two is 1. Now f of 4 is f of 3 plus f of 2. That is 2 plus 1. So this will give us the value 3. Now when you look at the right subtree, f of 1 is a base condition, it returns 1. F of 0 returns 0, it's a base condition. 1 plus 0, it will give you the value 1 for f of 2. And f of 1 is a base condition, it gives the value 1. So 1 plus 1, 2. So this gives 2. Now f of 5 is the sum of f of 4 plus f of 3. That is 3 plus 2. So this will give the value as 5. When we look at the algorithm for the implementation of Fibonacci series, so f of n, when n is less than 2, this forms a base condition. So the value of n, if it is less than 2, it means it is either 0 or 1. Then it returns the value of either 0 or 1. Otherwise, the function is recursively called with n minus 1 and n minus 2 term. The height of the solution tree is n, and at each level, that is level 0, level 1, level 2, and so on till level n. At each level, if you see, each function calls two subfunctions, that is f of 5 calls f of 4 and f of 3, that is n minus 1 and n minus 2. So at 0th level, the number of function calls is 2 power 0, that is 1, that gives 1. At the first level, it is 2 power 1, so that is the value 2. At the second level, it is 2 power 2, that is the value 4. At third level, it is 2 power 3, that is the value 8, and so on. Hence, the time complexity for this approach will be big O of 2 power n, that is 2 raised to n, which is an exponential time complexity. Now let us look at the space complexity. Initially, when the function is being called, the call stack is empty. Now f of 5 internally calls f of 5 calls f of 4 and f of 3. So what happens is, first the left subtree is created. So it keeps on creating recursively the left subtree till the base condition is met. So once the base condition is met, then the right subtree is created, and the value of left subtree and right subtree is added and returns to its parent. So f of 5 calls f of 4. So f of 5 is the calling function. It will be pushed into the call stack, and f of 4 is called. F of 4 internally calls f of 3, and while f of 4 is being pushed into the call stack. So this keeps calling till the base condition, that is f of 1 or f of 0 is encountered. So when f of 0 is encountered, right, so it returns the value of 0 and it is removed from the call stack. And f of 1, it returns the value of 1 and it's removed from the call stack. So this keeps on adding to the call stack and removing from the call stack. The functions gets called and removed from the call stack. So at any given point of time, the maximum number of calls in the call stack will not exceed n. So when f of 3 calls f of 1 and f of 2, f of 1 is computed, it is removed from the call stack, and then f of 2 is computed, removed from the call stack, then f of 3 Before it returns to f of 4 again calls f of 2. F of 2 is computed, returned, then f of 3 is computed, returned. So this keeps on going on till the final value, that is f of 5, is returned. So hence the space complexity will be big O of n. Now if you see 2 raised to power n, this is an exponential time complexity that has to be reduced to a quadratic form. So when you call this Fibonacci with 50th term, there will be 2 power 50 function calls, which is a very huge number. So this recursive function calls can be optimized by using dynamic programming. Why we need to go for recursion? Recursion is a very powerful problem solving strategy. It is a way of thinking about problems which can lead to simple and elegant solutions. Recursion adds clarity and reduces the time needed to write and debug code. How to implement recursion? First, let us look at the recursive implementation of our first example, the power function. I will be using Java to implement the code. So here I have written a template called as power, which takes two parameters, which is the base and the n value to which the base has to be raised. And also I have written, I am calling this function with 3 times with different parameters. First time I am calling power with 2 power 5, second time I am calling with 2 power 7, third time I am calling with 2 power 50. So each time the expected result is also mentioned in the comments. So let us go ahead and implement this method recursively using recursion. So here first I will add the base condition, that is if the value of n equals to 1, that is my base condition, then we'll say return the base. Otherwise we say return base into, call the power method with now the value of n decremented by 1, that is n minus 1. That is all to implement the power method. Let us see our code is correct or not. So we have the output here that is matching exactly with the expected output. Here we are going to implement the Fibonacci series for the nth term using recursion. I have already created a template. The name of the method is Fibo, which takes a parameter n. It has to calculate the Fibonacci series for the nth term. And also I am calling this Fibonacci series function Fibo with 3 times with 3 different values. That is Fibo of 5, Fibo of 7 and Fibo of 48. And the expected result is mentioned in the comments. So let's go ahead and implement this method. So here first we'll check for base condition, that is if n is less than 2, that is the value of n is either 0 or 1, then we return the value of 0 or 1. So if n is less than 2, we say return n. Else, no need of else because we already have a return statement. So here we'll say return Fibo of n minus 1 plus Fibo of n minus 2. That's it. Let us check whether our implementation is correct. Now when you see the Fibo of 5 and Fibo of 7, the expected result has come almost instantaneously, whereas for the Fibo of 48, it is still taking time. That means the implementation is correct, but it is not efficient. The reason being that when the Fibonacci series is being computed, the same subproblem which is already solved is computed again and again. Right now you see that we got the result. It took a while. That is, if a subproblem is already computed, no need of creating a subtree for that subproblem and computing again and again. So this is a brute force recursive approach. This can be optimized using dynamic programming. What are the issues with recursion? Recursion is usually slower due to the overhead of maintaining the stack. It usually uses more memory for the stack. And recursion is useful when a problem can be represented as a solution to its subproblems.